Hangouts on air is live. Okay, I'm seeing things that say live, but I'm looking at the, I see it. I see it live on YouTube. Oh my goodness. It worked. I can't tell if you can hear me though, because I am not using the monitor in something I can hear. So if you guys can hear me, please say something. Actually, one sec, let me test this. Does this go to chat? Question mark. Okay, that doesn't go to chat, so noted. Did it stop? Is it not live anymore? One sec, I'm gonna try a couple of different tabs. Like I said, I started going a little bit early to give myself a little bit of a buffer. Okay, so that's weird because it says that I am not getting a okay, so stream status is okay. Public view. Yes. And I hear my voice. Excellent. Okay, I think everything's good to go. I think it works. It works. I'm delighted. Welcome, everybody. We are finally going to be able to get back into this paper, which it's only been a week, but it feels like longer because I've had so many false starts and struggles with the live streaming, and I'm very, very, very delighted that everything is working. And look, it's 4 o'clock now, my time, and we're starting, and everything's great. Hopefully my audio quality isn't that bad. I'm using a different mic, and hopefully it still sounds okay, so let me know if that's a problem. And let's jump back into it. So this is the Language Models Are Unsupervised Multitask Learners paper, which is the GPT-2 paper. And you should see the link to this paper in the description. It's this one. It's awful. d4mucfpsywv.cloudfront.net/better-language-models/language-models.pdf is the link. And it is not on archive. It is just like a weird CloudFront hosting thing that they're doing. I don't know. And the premise of this paper is that they've built a language model, so sort of a probabilistic model of what words probably come next. And they are claiming that it can do a wide variety of NLP tasks without any specific training, without any labeled data. And you may have heard that they chose not to release this paper, the model that's described in this paper publicly. So that's something that we'll talk a little bit more about. I want to make sure that I get a chance to actually read the paper first so that I'm making informed decisions when I say things. So last time we read the introduction, and I noted that this is a paper that's not really in what's the word? Not discussion, but it's not really in dialogue with the NLP literature as much as it is with the machine learning literature. So something to note and notice. And then we read the discussion of the data collection, which was pretty sparse. So this section 2.1, where they discuss the training data set, is fairly small. And hopefully when we get down to the input representation, we'll have more examples of the data and what they talked about it. Because my impression, not having finished the paper, is that the major, what's the word I'm looking for? The major, not advancement, contribution of this paper is the fact that it has a very large training set, and that is what allows them to have such good performance. And I don't think it is necessarily a modeling improvement. So we should keep reading. But if that is the point, if that is the case, then the data set that they collected is one of the major contributions of their paper. And it's a little bit weird that they don't talk about it quite as much. But Let's keep reading. So we finished with section 2.1 last time, and we're starting with section 2.2, input representation. A general language model, LM, should be able to compute the probability of and also generate any string. Current large-scale LMs include preprocessing steps such as lower casing, tokenization, and out-of-vocabulary tokens, which restrict the space of modelable strings. Interesting. So the idea that you're able to compute the probability of a string of any sort of items is based on a lot of the work in information theory. So things like entropy and perplexity and how informative is this string? Are you very surprised or very non-surprised that given the words that you've seen previously, you get the next word? And they also claim that they should be able to generate any string, which is an interesting claim. I guess, yeah, theoretically, it's a little bit like the monkeys with the typewriters. And if you give enough monkeys enough typewriters, eventually they'll come up with Shakespeare just by pure combinations. Interesting. Not something I think everyone would claim about language models. Also, they mention that they include things like lower casing, which is not necessarily always something you want to do. And I have my previous research has shown that this actually removes social information, so that things like capitalization, punctuation, patterns of punctuation, especially in patterns of punctuation, can encode sort of more social nuance and meaning that you get rid of when you remove them. So something to think about. And this is a multilingual model, so they are going to talk a little bit about encoding. So while processing Unicode strings as a sequence of UTF-8 bytes elegantly fulfills this requirement, as exemplified in work such as Jillick et al. 2015, current byte-level LMs are not competitive with word-level LMs on large-scale datasets such as the 1 billion word benchmark. We observe a similar performance gap in our own attempts to train standard byte-level LMs on WebText. Okay, so they're saying we're using a word-level model rather than a character-level model. Byte pair encoding, Senark et al. 2015, is a practical middle ground between character and word-level language modeling, which effectively interpolates between word-level inputs for frequent symbol sequences and character-level inputs for infrequent symbol sequences. Wow. Despite its name, reference BPE implementations operate on Unicode code points and not byte sequences. These implementations would require including the full space of Unicode symbols in order to model all Unicode strings. This would result in a base vocabulary of over 130,000 before any multi-symbol tokens are added. So that would be like joining tokens, like a handshake can have different color skin tones associated with it. So once you include joining characters, you get more. This is prohibitively large compared to the 32,000 to 64,000 token vocabularies often used with BPE. Ryan Chesler says, was curious what WebText was. Yeah, I think that's their data set that they talked about for like a total of 200 words. And, oh, apparently somebody replicated it. Oh, interesting. Yeah, did they not? I mean, we haven't gotten to the end of the paper yet, but did they not release their data set? That seems, I mean, it is very large, so I see how that could be sort of a cost problem, but it is interesting that they chose not to share it. Blah, blah, blah. So talking about byte pair encoding, we don't want to do all of Unicode because it's big. In contrast, a byte-level version of BPE only requires a base vocabulary size of 256. However, directly applying BPE to the byte sequence results in suboptimal merges due to BPE using a greedy frequency-based heuristic for building the token vocabulary. We observed BPE to include many common words like dog, since they occur in many variations such as dog, 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 with different punctuation marks after it. This results in a suboptimal allocation of limited vocabulary slots and model capacity. To avoid this, we prevent BPE from merging across character categories for any byte sequence. We add an exception for spaces, which significantly improves the compression efficiency while adding only minimal fragmentation of words across multiple vocabulary tokens. All right, first off, let's check in with byte pair encoding again. I know that we've talked about it previously on this channel, but it is not something that I have used extensively, and I've forgotten what it was like. I know it's like one is different. Oh, right. So very, very frequent spans are replaced with smaller spans. Okay, that makes sense. So what they are doing is they are deciding, so the spans, each span is a member of the vocabulary, is what I'm getting from this. A byte level version of the BPE only requires a base vocabulary size of 256. So each byte is a vocabulary word. And then the applying BPE to the byte sequence results in suboptimal merges due to BPE using a greedy frequency-based heuristic for building the token vocabulary. So I guess what they're saying is that if in your training vocabulary, dog period, the word occurs more than something like signal processing the phrase, then it will say that dog period is very common, and it will give dog period its own token in the vocabulary, whereas signal processing might not get its own token in the vocabulary, even though at some level signal processing, like as a phrase, has a closer link to each other. And then we prevent BPE from merging across character categories for any byte sequence, with an exception for spaces. Oh, interesting. So by character categories here, I'm assuming they mean things like letters versus numbers versus punctuation and symbols versus emoji. So a BPE looking at this token that we are, so here in this sequence, we're replacing double A's with Z. The bytes can't be from different token categories, except they can be spaces. So we wouldn't be able to say like A space B, so that we could treat as a single token, but we couldn't treat A period space B as a single token because it has multiple categories in it. That's what I'm getting from that. I don't know if that's what they mean, but that's what I'm picking up. Not entirely sure if that's what they were putting down. Okay. So they're not using word level things. In fact, they are explicitly allowing tokens to cross word boundaries, but they are not allowing tokens to cross phrase boundaries and sentence boundaries, in as much as punctuation symbols and emoji can occur at those boundaries. And we know from other research that they do. Research that I would be surprised if these particular researchers had read, given the fact that they're not really talking much about the linguistics and NLP literature. Okay, the input representation allows us to combine the empirical benefits of word-level LMs with the generality of byte-level approaches. Since our approach can assign a probability to any Unicode string, this allows us to evaluate our LMs on any data set regardless of preprocessing, tokenization, and vocab size. Okay, so they're saying that the reason that they're not doing words is that if you are doing words, you have to have you have to commit to something that a word is, right? And you have to commit to pre-processing steps that are based on the wordiness, the quality of wordiness. So in theory, this could work equally well for any language that can be represented with Unicode strings, like Mandarin or Thai or Mongolian or I'm trying to think of an African language, Amharic, that has a very different non-Latin writing system, Russian languages that use Cyrillic. So I like that. That's sort of language agnostic, but I almost feel at this point that we're too language agnostic. Like there's a reason we do preprocessing. Anyway, let's keep reading. Model. So the input to our model is this byte pair encoding. So it's making our input data smaller, and rather than tokenizing, we're using these byte pairs that can include multiple words in a single sequence, but cannot include punctuation. And I am okay. So they're using. I don't know how many I don't know what their final token size was, like how many tokens they ended up with after doing the byte pair encoding. So we'll see if they talk about it. Model, we use a transformer, Vaswani et al. 2017. That's the Attention is All You Need paper. And if you're not familiar with it, we read it together. The last paper we read was the BERT paper, and then the one before that was Vaswani et al. Based architecture for our LMs. The model largely follows the details of the OpenAI GPT model by the same author, with a few modifications. So this is the OpenAI GPT model was one of the ones that we discussed during BERT that uses, I believe, one backwards facing and one forwards facing LSTM. Let me know in the comments if that's not right. I'm trying to pull it out of the oatmeal. So the modifications that they made were layer normalization, Ba et al. 2016, was moved to the input of each subblock, similar to a pre-activation residual network, Ke et al. 2016, and an additional layer normalization was added after the final self-attention block. A modified initialization, which accounts for the accumulation on the residual path with model depth, is used. Okay, I know some of those words. We scale the weights of residual layers at initialization by a factor of 1 over the square root of n, where n is the number of residual layers. The vocabulary is expanded to 50,257 tokens. We also increased the context size from 512 to 1024 tokens, and a larger batch size of 512 is used. Okay, so they ended up with a byte pair encoding derived vocabulary of a little over 50,000. These look like just parameter changes, the increase in context size and the larger batch size. Sound like just they made it bigger from the one that they had before. And I don't know what layer normalization is. Hit me up with this. No, I didn't want to print it. Cancel. Cancel. I wanted to search it. There we go. All right. Ba et al. 2016. That is the paper. I was hoping for something more like, let me zoom in a little bit so it's a little bit easier to read. Yeah, there we go. I was looking for like a blog post. I don't want to read the paper. Batch normalization, which I am more familiar with, is that you do normalization on the mini batch. But what is layer normalization? Layer normalization is a method developed by Geoffrey Hinton. And this is so small, bigger, even bigger. Compared to weight normalization, layer normalization is slightly harder to grasp intuitively. Let's learn more about weight normalization first. A method developed by OpenAI. OpenAI are the people who wrote the paper that we're reading now. The language models are unsupervised multitask learners. Instead of normalizing the mini batch, normalizes the weights of the layer. Weight normalization reparameterizes, the weights W of any layer in the neural network in the following way. Well, it's some math. The weights equal G divided by the extra square root of V times V. I don't know what the double lines mean. Similar to batch normalization, weight normalization does not reduce the expressive power of the network. What it does is separates the norm of the weight vector from its direction. It then optimizes both G and curly V using gradient descent. The change in learning dynamics makes optimization easier, as I have explained in the previous post. Well, I talked about batch normalization. You can tell that this was added to the blog post later because the font is different. All right, well, I don't have a good intuition of what that is, so let's move on because that's not the thing that they did. They did layer normalization. Okay, to understand layer normalization, recall that a mini batch consists of multiple examples with the same numbers of features. Got that. Mini batches are matrices, or tensors of each independent input is multidimensional, where one axis corresponds to the batch, and the other axis, or axes, correspond to the feature dimensions. Okay, with you so far. Batch normalization normalizes the feature input across batch dimension. The key feature of layer normalization is that it normalizes the inputs across the features. Okay. The equations of batch normalization and layer normalization are deceptively similar. I'm looking at these for where I can see the difference. So here it's minus the mean of I rather than the mean of J. Here we are summing across J rather than I. And here that's the same, where x sub ij is the I comma jth element of the input. The first dimension represents the batch and the second represents the features. I have modified the notation from the original papers to make the contrast clearer. The difference becomes a bit clearer when we visualize it. So in batch normalization, oh, I see. Okay. So we're, instead of normalizing the, so this is, let's see, so this is per example, and this is per feature. Yeah? Is that right? Somebody correct me if I'm saying the wrong things. Ryan says you swap the axes you normalize over. Yeah, that makes sense. Sorry, I'm thinking about why that would be better. In batch normalization, the statistics, blah, blah, blah. In contrast, in layer normalization, the statistics are computed across each feature and are independent of other examples. Okay, that means that layer normalization is not a simple reparameterization of the network, unlike the case of weight normalization and batch normalization, which both have the same expressive power as an unnormalized neural network. A detailed discussion of the differences this creates involves a lot of math that is beyond the scope of this article. So if you're interested, please refer to the original paper. Noted. So what I'm getting from that is that usually a neural network of sufficient width and depth that is wider in the middle can express any can express any function, but here what I'm getting from this is that if you're doing layer normalization, you can no longer express any function, and there are some differences. Ryan says, I don't generally believe in batch norm. In practice, it has almost never been useful to me. Noted. Have you used layer normalization? Has it been helpful? Advantage. The independence between inputs means that each input has a different normalization operation, allowing arbitrary mini batch sizes to be used. That seems useful. The experimental results show that layer normalization performs well for recurrent neural networks. Okay. Presumably, they're not going to publish papers about things that don't work well because we have the file drawer problem, which is where things that don't work don't get published, and sometimes people replicate that work because they don't know that it doesn't work. All right, though batch normalization is the most famous normalization method in deep learning, there are some key limitations that do not make it the best normalization method for all scenarios, namely that the batch size is set. Weight and layer normalization are both alternatives to batch normalization that have found their use in many domains. Hopefully, this post gives you a better overview of the differences between normalization methods and how to use them. Shed says layer normalization keeps features independently. Yeah, that's helpful. That's a good little summary. Yeah, I'm a little bit curious about the math about why that's different, but not curious enough to go read the paper. So that's what they did. They used layer normalization and not the weight normalization that was developed by their research groups. That's interesting. Layer normalization was moved to the input of each subblock. So each self-attention block, they have layer normalization at the beginning, similar to a pre-activation residual notebook. And an additional layer normalization was added after the final self-attention block. So normalizing over features rather than normalizing over observances. But doesn't that mean that you're assuming that the features are IID? Anyway, sorry. This is slightly out of my depth in terms of math. I'm doing a little dog paddle here. I've just got like my nose above the water. Okay, so they made some pretty small modifications. So they added a little bit of normalization. They changed the initialization. So if you'll remember from the BERT paper, in the BERT paper, they discussed how sometimes some initializations would result in a weird degenerate network, kind of, where it never, like the performance never got good. I don't know what it would be converging to, but it never like improved. And some initializations did. So maybe the this modified initialization is helping with that problem, although they don't talk about why. Ryan says, I haven't used layer normalization. Batch norm, in my understanding, was for very deep networks like ResNet with 152 layers. Otherwise, you just normalize the inputs and you're fine. Yeah, that makes sense to me. And then they scale the weights. So instead of normalizing it based on the number of residual layers. So the more residual layers you have, the smaller the scaling factor becomes. Sorry, I'm doing the movements with my hands. Yeah, so it looks like they did something a little interesting with their byte-pair encoding and their tokenization, except it wasn't tokenization. They did their own training data collection. And then they made some pretty small modifications from their earlier model, which don't seem to be, and none of these seem to be the main focus of this paper. So, experiments. We trained and benchmarked 4 LMs with approximately log uniformly spaced sizes. The architectures are summarized in Table 2. The smallest model is equivalent to the original GPT, and the second smallest is equivalent to the largest model from BERT. So it got bigger. Our largest model, which we call GPT-2, has over an order of magnitude more parameters than GPT. The learning all models still underfit WebText, and held-out perplexity has of yet improved given more training time. So they made the model bigger. They trained it for longer. Okay, that was weird. I just saw like a little zip where I just saw like a Kaggle symbol, and then it went back to this. Let me know if everything looks good for you guys. So their model's big, they trained it for a long time, and they hand-tuned learning rate for each model. That's a artisanal learning rate, little handcrafted learning rate in there. And they're not just memorizing the whole data set they're saying, and that as they continue to train, the held out perplexity continues to get better. So very big model, the longer it trains, the better it do. Language modeling. As an initial step towards zero-shot task transfer, we are interested in understanding how WebText LMs perform at zero-shot domain transfer on the primary task they are trained for, language modeling. Is that actually zero-shot task transfer if you just do the original task? I feel like that's just we trained a model for that task and then we tried it at that task. I don't think, I mean, by that definition, everything is zero-shot task transfer, right? I don't know, maybe I'm just not feeling their vocabulary choices. Since our model operates on a byte level and does not require lossy preprocessing or tokenization, we can evaluate it on any language model benchmark. Results on language modeling datasets are commonly reported in a quantity which is a scaled or exponentiated version of the average negative log probability per canonical prediction unit, usually a character, byte, or word. Results on language modeling datasets are commonly reported in a quantity which is a scaled or exponentiated version of the average negative log probability per canonical prediction unit. So perplexity, but modified for the size of the data set, I think is what they're saying there. We evaluate the same quantity by computing the log probability of a data set according to WebText LM and dividing by the number of canonical units. We evaluate the same quantity by computing the log probability of a data set. So just like the whole data set, like the log probability of the text, according to a WebText LM, and then dividing by the number of canonical units. So this is to account for the fact that if you're doing things at the byte level, there are more units to predict, and your prediction size is smaller than if you're predicting at the word level, I think is why they're doing this. For many of these data sets, WebText LMs would be tested significantly out of distribution, having to predict aggressively standardized text, tokenization artifacts such as disconnected punctuation and contractions, shuffled sentences, and even the string unc, which is extremely rare in WebText, occurring only 26 times in 40 billion bytes. So they're saying that we trained it on raw text, and we are comparing it to text that's been preprocessed. So in preprocessing, usually, excuse me. In preprocessing, usually punctuation marks are considered tokens in and of themselves. So you get spaces around them because tokenization is usually done on spaces, at least in English and English-like languages. Shuffled sentences. So in a lot of text data sets, you'll have one sentence per line. And even, thank you, Shed. Shed said, bless you. And even unc. So when you have a token that's out of vocabulary for many things, you will have the unknown token. And for the byte pair encoding, I think you would just have the original underlying byte strings, without the compression that you get from byte pair encoding, is my understanding. All right. And they're like, oh, unc doesn't really occur that much. We report our results in table 3 using invertible detokenizers, which remove as many of these tokenizing/preprocessing artifacts as possible. Since these detokenizers are invertible, we can still calculate the log probability of a data set, and they can be thought of as a simple form of domain adaptation. We observed gains of 2.5 to 5 perplexity for GPT-2 with these detokenizers. Are you going to talk about what those results are? Okay, so basically they're undoing the things that we do during tokenization and preprocessing. although they don't say specifically what things that they are changing that might happen during tokenization. And each tokenizer is going to do things differently. So in the BERT paper, we saw a tokenizer that I forget the name of. Anyway, that one. And different tokenizers make different changes. So hopefully they're using different tokenized. Okay, so what I'm getting from here is that we're not really comparing apples to apples. They're not doing text preprocessing, and they're also not looking at preprocessed text. They're sort of undoing the preprocessing to get back to basic text. And then they looked at a bunch of data sets. No training or fine-tuning was performed for any of these results. PTB, Penn Tree Bank, and WebText 2 results are from Gong et al. CBT, I don't know. Results are from Bajgar et al. 2018. Lambada results from Hoang et al. 2016, and Lambada perplexity results are from Grave et al. 2016. Other results are from Dai et al. 2019. So it looks like they just like grabbed some soda results from different papers that said they had soda. 2016 is a pretty long time ago in NLP. In 2016, I was still learning about n-gram language models. Ryan Chesler says Sentencebeast tokenizer is. Oh, thank you. That was the tokenizer from the BERT paper. Yes. Thank you. I don't know how much latency there is on this particular stream, but it seems to be quite a bit. So my apologies. I'm not ignoring you. It just we haven't caught up to each other in time yet. I guess I'm slightly from the future at this point. Okay. And then they are doing, okay, and they're also talking about different scores here. So it looks like this is perplexity. Perplexity, you want to be low. This is accuracy. Accuracy, you want to be high. This is BPB, and this is BPC. Byte probability, byte pretzel combinatorics. I do not know, but it looks like something where lower is better. Okay. Interesting. And then they talked about the different sizes. So the smallest model is GPT. So this model would be parallel to GPT. This model would be parallel to BERT. And then these are bigger than that. And sort of the thing I think that they want you to get from this is that the bigger the model is, the more likely it is to base the models that they are saying are currently state of the art. I'm not familiar enough with the space to say whether or not these actually are state of the art. It's interesting that they're not comparing to BERT, which I guess wasn't evaluated on these particular models. Okay. Interesting. Oh, they're still talking about this down here. WebText LMs transfer well across domains and data sets, improving the state of the arts on 7 out of 8 data sets in a zero-shot setting. Large improvements are noticed on small data sets such as Penn Tree Bank and WebText 2, which have only 1 to 2 million training tokens. Large improvements are also, these are also on very single genre text. So WebText, obviously Wikipedia, and Penn Tree Bank is based on the Wall Street Journal. Large improvements are also noticed on data sets created to measure long-term dependencies like Lambada, that's probably not how it is, and the children's book test. That must be what CPD is. So children's book tests, CN and NE. So maybe Chinese and Dutch, maybe? I Our model is still significantly worse than prior work on the 1 billion word benchmark, Chelba et al. 2013. This is likely due to a combination of it being both the largest data set and having some of the most destructive preprocessing. 1 billion word sentence level shuffling removes all long range structure. Ryan says, Sentencebeast tokenizer somehow has over 2K stars on GitHub, but only 5 citations. Something doesn't add up. I think what doesn't add up is that people who don't publish research are using it, or also people aren't publishing, aren't citing their packages. Cite the packages that you use. There's a really nice functionality in R for that. I think you could just say cite package name and it'll give you the citation in BibTeX format to stick in your biography. And I think there's a Python one as well. I just don't know what it is off the top of my head because cite, the function, is really memorable. 1 billion word sentence level shuffling removes all long range structure. Okay, but your language model should be able to handle one sentence. Like, it's good that you can do long range dependencies, but also you should be able to do sentences. Humans can do sentences, even in isolation. Okay, the children's book text, Hill et al. 2015, was created to examine the performance of LMs on different categories of words, named entities, nouns, verbs, and presuppositions. Also, named entities are nouns. Sorry, prepositions. I was going to be like, and presuppositions aren't a thing. Prepositions. Prepositions like in, on, of, and. Not and. And is a determiner. Oh, I think it's getting close to quitting time. Rather than reporting perplexity as an evaluation metric, CBT reports accuracy on an automatically constructed close task. Close is like BERT, where you do a hidden word, like a fill in the blank thing, where the task is to predict which of 10 possible choices for an omitted word is correct. Following the LM approach in the original paper, we compute the probability of each choice and the rest of the sentence conditioned on this choice according to the LM, and predict the one with the highest probability. As seen in Figure 2, performance steadily improves as model size is increased and closes the majority of the gap to human performance on this test. Data overlap analysis shows one of the CBT's test set books, The Jungle Book by Rudyard Kipling, is in WebText, so we reported results on this validation set, which has no significant overlap. That was actually my question, was whether or not these books were in the data set that it was trained on. Like, I am positive that they have Wall Street Journal articles in their training text if they're taking like millions of articles from Reddit. The likelihood that no one has linked from the Wall Street Journal from Reddit is infinitesimal. GPT-2 achieves new state-of-the-art results of 93.3 on common nouns and 89.1% on named entities. A detokenizer was applied to remove PTB-style tokenization artifacts from CBT. Pentry Bank. So Pentry Bank is probably the biggest and most well-known of all of the data sets that are made up of parsed sentences. So they show you the, let's see. Sorry for the weird acoustics of typing. Let's see just an image. There we go. So a parsed, oh, it's so small. Oh, it's so small. So parsing is something like this, where you deconstruct the dependencies of different words in a sentence and show constituency order. So basically, the heart of the matter is that the house at the end of the street is red of the street somehow has a closer connection. All of the words now have a closer connection cognitively to each other than street is red do to each other. So we can sort of like bundle these up together. And the task of determining what these dependencies are is called parsing, and Pentry Bank is a parsed data set based on the Wall Street Journal. And there are, different ways of thinking about how to do parsing, and I don't especially care to get into an argument about that, but feel free to hit me up on Twitter, and I will punt it to my friends who care more. Okay, so we got state of the art, yay, and near human performance they are claiming. Human performance are from Bajgar et al. 2016, instead of the much lower estimates from the original paper. Human performance are from Badger et al. 2016. Instead of the much lower estimates in the original paper. Okay, so I think that this is a, there was a paper, the original. So it sounds like they had other estimates of human performance in the original paper, and that these are revised estimates of performance. And of course, human performance on a task is not a monolithic entity. The Lambda dataset, Paperno et al. 2016, tests the abilities of sentence to model long-range dependencies in text. The task is to predict the final word of sentences, which require at least 50 tokens of context for a human to successfully predict. Oh, so this is going to be kind of similar to the co-entity reference resolution contest on Kaggle, because that's fairly long range as well. GPT-2 improved state-of-the-art from 99.8, Grave et al. 2016, to 8.6 perplexity, and increases the accuracy of LLMs on this text from 19% to 52.6%. Investigating GPT-2's errors shows most predictions are valid continuations of the sentence, but are not valid final words. This suggests that the LM is using the additional useful constraint that the word must be the final of a sentence. Adding a stop word filter as an approximation to this further increased accuracy to 63.24%, improving the overall state of the art on this task by 4%. Okay, so it's the final word of a sentence. You need at least 50 tokens to get it. GPT is finding words that could work but aren't final words. Thank you, Shed. I'm going to try to be better about muting when I have to sneeze. But it's one of the things, like, as soon as I mute, I'm not going to have to sneeze anymore, right? So they changed it a little bit. So the thing that it is mostly predicting are valid stop words. So stop words are very common words like and, of, the, a lot of prepositions that happen so often that they are often removed. They happen so often that they are removed from most preprocessing tasks during preprocessing for a lot of tasks because they're not semantically informative. And it looks like GPT-2 is often saying it's a stop word. Removing that increases accuracy by quite a bit. The previous state-of-the-art, Huang et al. 2018, used a different restricted prediction setting where the outputs of the model were constrained to only words that appeared in the context. For GP2, this restriction is harmful rather than helpful, since 19% of answers are not in context. We use a version of the dataset without preprocessing. So again, they're using a different data set for their evaluation than the other people that they're evaluating against. I don't know how I feel about that. On the one hand, I absolutely agree that preprocessing can remove useful information. But on the other hand, if everyone else is using preprocessed text and you're choosing not to, that seems... But like eventually we would like to be able to not have to do preprocessing. But it's not quite apples to apples, is it? It's kind of like apples to crab apples. Anyway, and then they're going to talk about... so we're still going through... Okay, so this is all of the things that they've talked about so far. So the Lambda long-range dependency data set, looking at both perplexity and accuracy. The CBT, the children's book text, CN and NE. It still doesn't say, I still have no idea what CN and NE mean. Presumably one of them means without the Jungle Book, I'm guessing. Looking at accuracy, which goes up. WikiText 2 and the Penn Tree Rank, bigger models do better. English Wiki 8, Text Wiki, Text 8, I still don't know what these are. Presumably we'll get to there. WikiText 103 and then the 1 billion word corpus that they did not do good on. And they say that that is because the sentences are shuffled. Reading comprehension, is that where we are? No. Winograd Schema Challenge. Performance on the Winograd Schema Challenge, Schema, as a function of model capacity. Okay, so more parameters makes better. Ryan says, looked up some of the models they compared against. One was Transformer XL. Why they couldn't put that in the table, I don't know. Each state-of-the-art column might be a different model, and we don't know which one. So they do say some of them. Although it just sort of says where the results are from and not which specific one that they're talking about. I guess what you could do, and you shouldn't do this, but what you could do is say that the results are from this paper and then take like the bad baseline results that they were like, we beat these, and be like, these are the results that they said about in their paper. I'm sure they didn't do that, but that would be a bad thing to do and you shouldn't do that. Okay. The Winograd Schema Challenge, Levisque et al. 2012, was constructed to measure the capability of a system to perform common sense reasoning by measuring its ability to resolve ambiguities in text. Recently, Trin and Lee, 2018, demonstrated significant progress on this challenge using LMs by predicting the resolution of the ambiguity with higher probability. We follow their problem formulation and visualize the performance of our models with both full and partial scoring techniques in Figure 3. GPT-2 improved state-of-the-art accuracy by 7%, achieving 70.70%. I don't know why there's a trailing zero there. The dataset was quite small with only 273 examples, so we recommend reading Triclier et al. To help contextualize the result. That's cheating. It's a common sense reasoning challenge and you're just guessing the most likely thing. I feel like you're not approaching these challenges in the spirit in which they were constructed. Shrishti Yadav says, the paper came out in August last year. The citations might increase in future. I don't know which paper that was. This one that we are reading now, like just came out. I don't know if that's what we were talking about. Okay. Well, so guessing the most likely thing can get you up to 70% accuracy, and they're upset that it's a small data set. And I think this is Karen, one of Karen's data sets. Levisque. Oh no, it's not. I'll make this bigger. A Winograd schema is a pair of sentences, schema, that differ in only one or two words that contain an ambiguity that is resolved an opposite way in the two sentences and requires knowledge, use of world knowledge and reasoning for its resolution. The schema takes its name from a well-known example by Terry Winograd. The city councilman refused the demonstrators a permit because they feared/advocated violence. So it could be the city councilmen that are fearing the violence or the demonstrators that are advocating the violence. Hector Levisque, I thought it was somebody else, proposes such a set not solvable by simple techniques such as selectional restrictions. Google proof there's no obvious statistical task over text corpora that will reliably disambiguate them correctly. Turns out this paper, they didn't reliably disambiguate them correctly. Yep, and there's a grand prize of $25,000 to the first contestant who achieves 90% accuracy on both ends of the rounds of the contest. So they ain't there, and I feel like you cannot complain that the data set is small in this particular situation. Scroll. Okay. Reading comprehension. The conversation question answering dataset, COCA, Ready at All 2018, consists of documents from 7 different domains paired with natural language dialogues between question asker and an answer. Oh my gosh. COCA consists of documents from 7 domains paired with natural language dialogues between a question asker and a question answerer about the document. COCA tests reading comprehension capabilities and also the ability of models to answer questions that depend on conversation history, such as why. Did that really come out in 2018? I feel like it's been around longer, but maybe that's just because people talk about it a lot. Greedy decoding from GPT-2, when conditioned on a document, the history of the associated conversation, and a final token A, achieves 55 F1 on the development set. I don't know what greedy decoding is. Let's look that up. The greedy search decoder and how to implement it in Python. Trainable greedy decoding for normal machine translation. Here we go. This looks like a lecture slides. Big. It's a tutorial. Fantastic. Tell me about the greedy decoding. Window approach. So the idea is that you look at a word. I don't know what any of these things stand for. Okay, so they did some sort of parsing thing, is what I'm getting from this. CCG, no part of speech feature, reduces word sparsity, global context information. I forget what it is. Something context grammar. But whatever, excuse me, drop my glasses. Whatever the first C stands for. Constituent parsing with recursive and neural networks, recurrent neural networks. All right, well, this is a whole can of worms I'm not super familiar with and don't want to start eating now. So they did greedy decoding. When conditioned on a document, the history of the associated conversation, and a final token A. So they look at the whole document, the previous part of the conversation, and the last thing that was said, achieved 55 F1 on the development set. This matches and exceeds the performance of 3 out of 4 baseline systems without using the 127,000 plus manually collected question answer pairs those baselines was trained on. The supervised state-of-the-art, a BERT-based system, Devlin et al., is nearing 89 F1 performance of humans, F1 goes up to 100. While GPT-2's performance is exciting for a system without any supervised training, some inspection of its answers and errors suggests GPT often uses simple retrieval-based heuristics such as answer with a name from a document in response to a who question. Oh, so if somebody asks who, they just answer with one of the names from the document, whether or not that's correct. Oh, looks like you do know something about the existence of named entities, after all. All right. Let's read session 3.6 and then call it a day because it is almost 5 and I got something this evening that I got to do. Summarization. We test GPT-2's ability to perform summarization on CNN and Daily Mail dataset, Nalapati et al. 2016. To induce summarization behavior, we add the text TLDR after the article and generate 100 tokens of the top K random sampling, where K equals 2, which reduces repetition and encourages more abstractive summaries than greedy decoding. We use the first 3 generated sentences in these. I don't think they're actually doing what I thought they were doing. I think they're just using the language model as the input to the encoder, and then the decoder, it just means that they're taking the most likely next token given their given their model. We use the first 3 generated sentences in these 100 tokens as the summary. While qualitatively the generations resemble summaries, as shown in Table 14, they often focus on recent content from the article or confuse specific details, such as how many cars were involved in a crash or whether a logo was on a hat or a shirt. On the commonly reported Rouge 1-2L metrics, the generated summaries only began to approach the performance of classic neural baselines and just barely outperformed selecting 3 random sentences from the article. GPT-2's performance drops by 6.4% on the aggregate measure when the task hint is removed, which demonstrates the ability to invoke task-specific behavior in a language model with a natural language. It's hallucinating facts. It's making things up. It's just sort of, this is not knowledge representation. This is not semantics. Okay. The value of this paper, what I'm getting from it so far, is that it's a nice demonstration of some areas where just bigger and more is not necessarily going to get you to the point where you would like to be eventually. It seems many of these tasks are not, like, there's no world knowledge here, right? There's no semantics. This is all saying the most likely things, right? Ryan Schessler says, oh, greedy encoding is opposed to beam search, I believe. When k equals 2, they're doing beam search instead of just picking the best option. Gotcha. That makes sense. Yeah, I'm going to take some time to process my feelings and talk about them in a better way. I don't know. I'm frustrated by this. Yeah. I agree that they get better results on some tasks, and those results get better as they do bigger. But I don't necessarily think that represents. No, I don't know. I'm not an engineer. I'm a scientist, and I want, I want why, and I want models, and I want interpretability, and I want structure in my data, and this is not those things. Anyway, I'm going to take some time to process. We're not done with the paper yet. We've got yeah, we're probably going to be done with this next time, looking at how much we have left. I mean, famous last words. If we get distracted by more things like layer normalization, we will we'll talk about that. If we get distracted by things like layer normalization, we'll take a longer time to get through it. But for now, I think I'm going to call it. We will resume with the translation section. I'm glad that they talked about the things that they did in the summarization section, specifically that it's fluent, like it looks like real language, but the things that are said are wrong. They don't reflect world knowledge and the actual they don't reflect common sense in an NLP sense. Okay, so I'm gonna try and figure out how to end this. Sorry, this is the first time I've, is it this one? Yeah, this one. All right, I'm gonna call it there. We will resume section 3.7 next Wednesday morning at 9 a.m. Because we have a workaround here, and I have ordered more parts, and I'm gonna do some computer stuff, and hopefully it'll work. And that'll happen soon. But if you've had to buy graphics cards recently, you know what a pain that can be. Yep, so I will be back on Friday with live coding at 4 p.m. Pacific, which is 7 p.m. Eastern, and I don't know what time in India. And if you're here then, I will talk to you then. And if not, I will talk to you next Wednesday morning. Thanks so much for joining. And ooh, yeah, keep your eyes peeled on Monday. I've got another Kaggle coffee chat that I think will be very relevant to this paper. And I'm looking forward to sharing that with you guys. Yeah. Oh, and Kaggle Days is also coming up in, we've got 2 that are coming up. We've got one in San Francisco that I'm going to be at. That's because I'm also going to be at Next, the Google conference, and they're happening at the same time. And then we also have one at Dubai, which is slightly after then. I want to say it's April 30th, maybe. Go look it up. We tweeted about it. And I am really looking forward to hanging out with you guys there. All right. Have a really great day, and I'll talk to you later. Bye.